This video is recorded to help my students to understand how to sketch the graph of a function. Today I will use a polynomial fx equal x to the third minus 3x squared minus 9x plus 27 as an example. Again, we will follow the following 8 steps. First, we find the domain of the function. Then we find the intercepts and plot those intercept points. Then we find the asymptotes and sketch them using dashed lines. Then we find the critical points that are the candidate points for local extrema. Then we determine the intervals on which the function is increasing or decreasing, hence determine the local extrema and plot these local extrema points. Then we find the candidates for inflection points. Then we determine the intervals on which the function is concave up or concave down. Hence, we can determine which candidate is actually an inflection point. Then we plot those inflection points. After we finish these 7 steps, we should have enough information to sketch the graph of the function. We can sketch the graph by using smooth curves to connect the plotted points. We just need to ensure that the domain, asymptotes, local extrema, increasing and decreasing property, and the concavity are reflected in the sketched graph. Okay, let's start from the first step to find the domain of the function. Since this function is a polynomial, say its domain is all real numbers. So we just say the domain is all real numbers. Of course, the student need to know how to write this in interval form, is from negative infinity to positive infinity. Then we find the intersection point. We need to find the x-intercept and the y-intercept. To find the x-intercept, we just need to solve fx equals 0. So in this particular problem equivalent, we need to solve x to the third minus 3x squared minus 9x plus 27 equals 0. We will solve this by using factoring. To factor this, I first group x to the third minus 3x squared together. Then I group 9x minus 27 together. Okay. Now we know we can see each group I can factor it. For the first group, I can factor out x squared. Then I have x minus 3 left. For the second group, I factor out 9. I have x minus 3 left. Then we know x minus 3 is a common factor of both groups. Then I can factor x minus 3 out. I have x squared minus 9 as another factor. Now I continue factor x squared minus 9. Then I will have x minus 3 multiply x minus 3 multiply x plus 3 equals 0. Solve this, we will get x equals 3 or x equals negative 3. Now, from here, we can conclude that the graph will pass through points. One point is negative 3 and negative 3 and 0. And another point is 3, 0. Now, if you pay attention, x equals 3 is a 0 of multiplicity 2. That means the graph of this function will not cross x-axis at x equals 3, only touch it. This is some knowledge from college algebra. Okay. Now we need a third step, find the asymptotes and sketch them using dashed lines. The fact is a polynomial doesn't have asymptotes, so we just say there is no asymptote. However, the polynomial has end behavior. It's easy to determine. As x goes to infinity, the fx goes to positive infinity. As x approaches to negative infinity, then fx also approaches to negative infinity. These are the end behavior. It's easy to see. Next step, we will find the critical point, which are the candidates point for local extrema. To find a critical point, we need to solve f derivative equals 0. So let's first calculate f derivative. F derivative is just 3x squared minus 6x minus 9. I need to solve this equals 0. To solve this equals 0, you can simplify it first if you wish to, or you just directly factor 3 out. For example, I would like to simplify it, so I divided 3 both sides. So I got x to the square minus 2x minus 3 equals 0. That will give me x minus 3 multiply x plus 2 or x plus 1 equals 0. So that's give me the solution, which is x equals 3 or x equals -1. So we have two candidates for local extrema, x equals 3 or x equals 1. Then as those two candidates are local extrema, we need to determine this. So we need to determine the intervals on which the function is increasing or decreasing. If the function increases first then decreasing, we just pass through a local maximum. If the function decreases first then increasing, then we just pass through a local minimum. That's why we need to determine on which interval the function increasing or decreasing first, then we can determine those two candidates if the local maximum or local minimum. In order to do so, I can build a table. I will build a 6 column, 3 row table. Everything in the middle? Oh, no, that's not really what I want. I want everything in the table to be located in the middle, okay? So first I want x. Then the first one is the interval from -infinity to -1. Then I will have a -1. And the next one is the interval from -1 to 3. Then I will have point 3. Then for next interval, I will have from 3 to +infinity. Okay. Then I need to have f derivative. I need to check on those intervals, what is f derivative? Is it positive or negative? Now, you see, when x from -infinity to -1, you can easily say this is positive. Well, because his derivative is a quadratic function open up. As x goes to -infinity, this function value will be positive. Of course, so on this interval, the f derivative will be positive. At this point, f derivative is 0. In this interval, you want to decide if f derivative is positive or negative. You can pick 0 as a test point, plug into this first derivative. You say when x equals 0, the first derivative is -9 is negative. So at this point, is negative. Then at this point, derivative is 0, and in this interval, derivative is positive again. Again, we can say in this interval, as x goes to infinity, this first derivative goes to infinity. Of course, it's positive. So on this whole interval, the first derivative is positive. After we determine that, it's easy for us to check this is increase or decreasing. First derivative is positive, is increasing. First derivative is negative, is decreasing. First derivative positive is increasing. Now the function increasing first, then decreasing. So this point is local maximum. And for here, function decreasing first, then increasing. This point is local minimum. Okay? And we actually can calculate the local maximum. Local maximum is f negative 1. This is easy to calculate. That will just be f negative 1 is just 32. Okay. Okay, let's see. In the step 2, we forgot one step to find the y-intercept. Okay. To find the y-intercept, we just need to evaluate f0. f0, which is 27. So we can say the graph passes through point 0 and 27. This is some step we miss at step 2. Well, now I fix it. Okay, so we got the local maximum is this, and the local minimum if you find this will be f3, and this will equal 0. Because from the previous step we know 3 is a x-intercept, x equals 3. Now, next step we find the candidate for the inflection point. The candidate for the inflection point is the point that is the x value that the second derivative not exist or second derivative equals 0. So we try to calculate the second derivative. The second derivative is just the derivative of the first derivative. So 3x squared minus 6x minus 9, this first derivative, we take derivative. The result is the second derivative, minus 6. I want to solve second derivative equals 0, so which give me x equal 1. So x equal 1 is a candidate for inflection point. In order to determine it is an inflection point or not, we need to again insert a table. This time the table I want it to be 4 column and 3 row. So 4 column and 3 row. Again, I want everything in the middle, so it's have a good look. Okay, so again I will have x. Then the one part is the interval from negative infinity to 1, and this is a candidate point 1, and this interval from 1 to positive infinity. Now, on each interval, I want to check what is the sign of second derivative. Well, since the second derivative is 6x minus 6, when x is less than 1, 6x minus 6 is negative. So we know for this part is negative. At x equal 1, second derivative is 0. From 1 to positive infinity, second derivative is positive. So that means this function fx on the interval from negative infinity to 1, this function is concave down, since the second derivative is negative. Now, on this, it is concave up. So it's concave down first, then after passing through this point, it becomes concave up. So the point, the x value, x equal 1, that is an inflection point. Okay, so the inflection point, we need to calculate his y value, y coordinate, which is f1. So f1 is easy to calculate. That will be 16. We can calculate f1 equals 16. After we done this 7 steps, we have all the information we need to sketch the graph. So we connect all those points, we will get the graph like this. Look at this graph. It reflects all the information we get from step 1 to step 7. First, you can see the functions domain is all real numbers. then you can say the x-intercept is x equal -3 and x equals 3. And notice x equals 3 is a 0 of multiplicity 2. Then the function graph will just touch x-axis at x equals 3, but will not across it. Then the y-intercept is 27. And then we found the function graph will increase from -infinity to -1. From -1 to 3 will be decreasing, and from 3 to positive infinity will be increasing again. Those we found the local maximum at x equals -1 and the local minimum at x equals 3. We also found that the function will be concave down from -infinity to 1 and concave up from 1 to positive infinity. And this, when x equals 1, this point 116, x coordinate is 1, y coordinate is 16, is an inflection point. So we got a correct graph sketch. If you have any questions, please give me an email. Goodbye.